Hello, today we are going to talk about section 1.2 in Review for College Math. Today is all about symbols and sets of numbers. So here we go. A set is a collection of objects. The objects in the set are each called a member or an element. Usually we do call them members. Some things that we have here in notation, the braces. They're kind of difficult to make for some people, but practice makes perfect. So just a little curl and a little curl. Okay, so when we talk about the different sets, the first set of numbers that we talk about is the natural numbers. This is the numbers that we count with normally: 1, 2, 3, so on and so forth. The next set of numbers is the whole numbers. This is the natural numbers and 0. So 0, 1, 2, 3, and so on and so forth. The integers are the next set of numbers. This is the whole numbers and their opposites. So negative numbers, okay? No decimals or fractions or anything yet. That is what comes next, the rational numbers. The rational numbers is a set of numbers that can be written as a fraction or a decimal that ends or repeats. Some rational numbers, some examples for you. We've got 2. It's rational. We've got 1/3, which, if you think about it as a decimal, is 0.3 repeating. So anything that can be written as a fraction or a decimal that repeats or something that ends, -3.25. Common one. All right. Next we have irrational numbers. Irrational numbers will be numbers that cannot be written as a quotient of integers. That means a fraction, or a decimal that never ends and never repeats. That's an and there, okay? So some examples. One we see a lot, pi. The number e. We'll talk more about that one later in this class. Some other ones, the square root of 7, because we don't know what that is. It's a decimal that never ends or never repeats. Some of you are thinking, oh, but I can put that into my calculator. Well, when you put it into your calculator, it rounds it off. You do not get the entire value of square root of 7. So that is an irrational number. Next, we have the set of real numbers. This is our last set. It's the set of numbers that can be represented on a number line. This is basically, until we get to the last chapter of this book, this is going to be every single number we have. So if you're asked to divide the numbers into what groups they belong, every single number will be a real number. Okay? All right, our last vocabulary word for today is mathematical statement. A mathematical statement will contain one of the following verbs, and it can be true or false. So the verbs that we have, they're kind of small here, but you can see them. Equals, not equals to, approximately equal to, less than or equal to, greater than, and greater than or equal to. All right, so here we go. We are going to go through a few examples for you. Place an inequality symbol to make a true statement. Now, there are several different answers that will work correctly for you here. I'm going to place all of the answers. So 2 is less than 3, is less than or equal to 3, or not equal to 3. Some of you are thinking, why can't we use approximately equals to? 2 is not approximately equal to 3. If we were to say $2 million and $3 million, they are not approximately equal. Something like 2.1 and 2.11, those would be closer to approximately equal to. All right. 7 is greater than 4. Oops, wrong symbol. 7 is greater than 4. There we go. Greater than or equal to 4 and not equal to 4. Now over here we have the same sentence but flipped, so our symbols will also flip. 4 is less than 7, less than or equal to 7, and not equal to 7. All right. Here we go. Tell if this statement is true or false. 8 is greater than or equal to 8. True. Letter B. 23 is less than or equal to 0. This is not true. 23 is greater than 0, so false. And letter C, 23 is greater than or equal to 0. This is the correct statement from letter B. Translation. So what we're going to do here is simply take the words and write them as a mathematical statement. So letter A, 9 is less than or equal to 11. Letter B, 8 is greater than 1. And letter C, 3 is not equal to 4. Using the following set, what we're going to do is place the numbers into which sets they belong. So, starting with -2. -2 is not natural, but it is not whole, and it is an integer. It is rational, and it is real. We next have 0. 0 is a whole number. It's the first whole number. It is an integer. It is rational. It is real. Everything is real. Don't forget that. 1/4 is a fraction, which is rational and real. -1.2 is a decimal that ends, so it is rational and real. 112, it's a natural number. Put it over there. It is a whole number. It is an integer. It's rational and it is real. -3 is an integer, rational, and again, real. Everything is real today. 11, natural, whole, integer, rational, real. Our last one, radical 2. Radical 2 is one of those numbers where we don't know what it is. It's a decimal that never ends and never repeats. That will make it our only irrational number, but it is still real. All right, last thing that we're going to do on this is go ahead and graph all of these numbers on a number line. So when you do this, you need to put your values in and make sure that you do try to keep things evenly spaced and numbered. Let's see, my 0 seems to be a little bit large here, so let's fix that up. There we go. All right, so let's place these values. So we've got -2. It's going to come down right there. Normally what we do is we will place a point to represent that. Kind of missed a little there, but my pen's off. All right, next up we have 0. I'm just going to label them all first. 1/4, slightly bigger than 0. Okay, just slightly bigger. We got some space issues here. -1.2, slightly bigger than -2, but less than -1. 112. Now 112 isn't going to fit on my number line, so I'm just going to kind of place it out here, and I'll put a break in the number line in a moment. -3, bring it on down. 11. So we stopped here at 4, 5, 6, 7, 8, 9, 10, and 11. And radical 2. The easiest way to deal with radical 2 is to pick up your calculator and punch it in and get a decimal equivalent for today's purposes. So it's between 1 and 2. We're just going to put it right about there. Go back in and let's put some points. So here we go. And 1/4 will be slightly over the line there. Not very good at drawing today, I guess. And 112. So again, putting a break in the graph. So to represent that break, we're just going to go and continue on out. All right. Our last bit here is absolute value. It's the distance a number is from 0 on the number line. Keep in mind, distance is always positive. You can go in a negative direction, but your distance traveled is positive. So the notation is these bars that you see here. And our few examples here. The absolute value of -3. The distance from 0 is 3. Letter B is the absolute value of 0. Well, 0 is 0 from itself. And the last thing we have is the opposite. That's what this little negative out here is. The opposite of 4. Opposite of the absolute value of 4. So it's -4 because you're saying the absolute value of 4 and then taking the opposite value of that. Thank you for listening. Have a good day.